For generations, people have wondered about the Earth. How can mountains grow? And living creatures be turned to stone? How can a planet covered by cool oceans be hot enough inside to shine like a star? Join us in a search for the heat within the Earth. It has transformed the surface over billions of years. Even now, this heat is bringing into being a very different world of tomorrow. The heat within, this time on the Miracle Planet.
Hello, I'm Bill Curtis for the Miracle Planet. Every year, thousands of people come to Yellowstone National Park to see the geysers, the hot springs, and the mineral terraces. But as dramatic as Old Faithful and the Minerva Terrace may be, even more amazing is the power that drives them. Beneath the Earth's crust, there is a sea of molten rock, which heats groundwater and forces it to the surface. This water is turned to steam and mixed with minerals to produce the marvels that have made Yellowstone famous. Although the Earth's internal heat is not always so dramatically displayed, it is still apparent all over the world, from the highest mountains to the deepest oceans. But what is the Earth like deep beneath the surface? We can't really travel to the core as Jules Verne imagined in Journey to the Center of the Earth. But there is one place where we get a sense of the Earth's interior heat.
This is the Western Deep Levels Mine in South Africa's Witwatersrand. Less than 50 miles from Johannesburg, this mine tunnels as far beneath the Earth's surface as many mountains stand above it. The lure of gold is the driving force in this venture into the Earth's interior. A century ago, gold was mined near the surface, but today in South Africa, it is mainly found in ultra-deep deposits. To reach the bottom of the Western Deep Levels Mine, elevators plunge downward at a speed of 25 miles an hour. At the end of their journey, the miners arrive 11,738 feet below the surface. This literally is the deepest point in the world to which humans have ventured. The greatest challenge to mining at this depth is not the lack of air or threat of cave-ins. It's the heat. Drilling into the rock reveals why. Just beneath the surface, the temperature is 52 degrees Celsius, hot enough to burn the naked hand. Yet Western Deep Levels Mine is a mere scratch in the uppermost layer of the Earth. The labyrinthine tunnels of the gold mine are insignificant when compared to the vast interior of the planet. Beneath the Earth's crust, liquid outer core, and at the center of the planet, an intensely hot and dense, solid core. Deep within, the Earth reaches a hellish temperature of 11,000 degrees Fahrenheit. Beneath the surface of our mild, temperate world is an inferno. A mere 30 miles of hard rock separates the surface from the hot interior. How did the Earth develop in this way? To understand, we must return to the dawn of planetary time, billions of years ago. In that primordial era, planetesimals rained down on the Earth. The energy released by their impacts eventually turned the surface into a red-hot sea of molten rock. Deep within the Earth, a tremendous amount of heat was generated by naturally occurring radioactivity. This nuclear furnace, fueled by radioactive decay, turned the inside of our world into a molten mass. More than 4 billion years later, the interior of the Earth continues to generate enormous heat, which rises toward the surface and in some places breaks through the thin, cool crust. Iceland is one such place. Despite its name, Iceland is the world's largest volcanic island. Much of the land is covered by glaciers, but the snow and ice blanket the true origins of the landscape. Beneath the ice, the land has been formed by lava from repeated volcanic eruptions since prehistoric times. This volcanic heritage is particularly evident at Lakagigar crater, actually a row of craters. In 1783, Lakagigar was the scene of an immense eruption which killed half of Iceland's livestock and 1/5 the human population. Iceland is still volcanically active, with an average of 1 major eruption every 5 years. Unusual formations on the landscape testify to this ongoing process. When lava cools, it sometimes cracks into hexagonal columns as much as 65 feet tall. Iceland is an extraordinary island where fire and ice exist together. Underground hot springs melt glacier ice, creating streams that in turn become rivers. The rivers have their source in caves beneath the glaciers. Here the cave extends for over a mile, and the water is pleasantly warm. In fact, even though there are tons of ice overhead, the hot water makes this a comfortable place for bathing. The heat beneath the surface finds release in a variety of ways. In recent years, the center of activity has moved from Lakagigar to the Krafla area. Here, Dr. Gudmundur Sigvaldason observed the beginning of an eruption on September 4th, 1984.
There had been 2.5 years without any eruption in this area, and we knew that the magma reservoir, the magma container down at 2.5 kilometers depth, was under very high pressure. Then suddenly in the evening at about 8:30 in the night, then we heard that there had been a sudden pressure release. So we knew that the magma was on its way to the surface.
Within minutes, the night was in flame, and Krafla transformed beyond recognition. In the beginning, there were 2 distinct curtains of fire, but they joined as the eruption grew. Soon, lava was erupting 500 feet in the air and spreading out over a 5.5-mile front. The searing heat of the Krafla eruption churned the cold night air into violent tempests. The surface lava was swept up into burning cyclones. Hellish vistas like this, first witnessed by 9th century Viking explorers, must have evoked terrifying visions of doomsday. Actually, this is a picture of birth as much as destruction. Flows like this, spreading again and again over millions of years, are what formed Iceland. On layer after layer of lava, this island has risen above the surface of the ocean. The 1984 eruption at Krafla lasted a week, leaving behind a row of smoking craters. The eruption occurred along a fissure, where the earth cracked open in a long line. Fissures are found in many parts of the world where volcanic activity occurs, but nowhere on land are fissures more common than on Iceland. This is the largest Icelandic fissure, called Thingvellir. It opened up a gash 25 feet wide and cut the rocky landscape to a depth of more than 50 feet. Thingvellir is unmistakable evidence of the heat within the earth and the enormous power unleashed when that energy escapes. The major volcanoes of Iceland rise in a line extending from the northeast to the southwest. The island's fissures run in the same direction and continue off the land into the sea. In 1974, far south of Iceland near the Azores, French and American scientists began exploring the floor of the Atlantic Ocean. At a depth of 10,000 feet, they found the ocean floor to be much different than they expected. It was littered with strange, round rocks. Similar rock formations had been previously discovered off Hawaii, when lava flowing from a volcano poured into the ocean. It was named pillow lava. The characteristic pillow shape results from the sudden chilling of the lava when it contacts seawater. This pillow lava was found at the bottom of the Atlantic. It proved that this portion of the ocean floor had been volcanically active. No sediment had yet settled on the rocks, indicating that the activity was recent. Soon, evidence of undersea volcanism was discovered on the other side of the world. In 1977, the American research submarine Alvin was involved in another historic ocean floor exploration. This time, the site was the Eastern Pacific, where at a depth of 8,500 feet, researchers came upon something quite unexpected. In the faint illumination of their lights, the submarine crew saw a forest of eerie chimney-like structures, which seemed to be emitting dark clouds of smoke. Although they are called black smokers, the billowing discharges actually proved to be superheated water, colored by particles of metallic minerals. The chimneys themselves are made of solid mineral deposits that precipitated out of the water, primarily iron, zinc sulfide, copper sulfide, and silver. Another surprise was the incredible abundance of life in and around the black smokers. Here, in what to us are almost unimaginably hostile conditions, anaerobic bacteria thrive and provide the foundation for a rich food chain. Further north in the Pacific, off the coast of British Columbia, Canadian researchers found new types of smokers. They discovered vents where the discharge was white and even colorless. Like black smokers, they were intensely hot. In this case, 294 degrees Celsius, hot enough to melt lead. Evidence from around the globe indicates that certain regions of the ocean floor are volcanically very active. Survey work in the Eastern Pacific, off the coast of Mexico, provided data to construct a model of the ocean floor and a high mountain range running north to south. Volcanic activity in the ocean is centered on this undersea range and the deep valley that runs along the crest. The valley walls are shaped like steps and marked with volcanic fissures. The ocean floor is studded with smokers, indicating continual geothermal activity. Increasingly, evidence points to the conclusion that there is more volcanic activity on the seafloor than on dry land. In fact, underwater volcanism has been observed along undersea ridges in the Atlantic Ocean, in the Red Sea off the coast of Africa, and all along the Pacific coast of the Americas. The heat within our planet is constantly flowing toward the surface. This is what forces up the ocean floor and causes fissures in the surface. Through these mountains at the bottom of the ocean, the heat within the earth is continually released. A reservoir of molten magma rises close to the surface beneath the mid-oceanic ridge. The magma heats the rock on either side and is responsible for the new lava that is constantly being erupted. The seafloor is dissipating heat as it spreads away on each side of the mid-Atlantic ridge at less than an inch per year. But some points along the mid-Pacific ridge are spreading 9 times that rate. Undersea mountain ranges stretch almost continually from off the coast of Mexico, across first the Pacific and then the Indian Ocean. The ridge continues around the Cape of Good Hope and northward through the Atlantic Ocean. This 45,000-mile-long volcanic range serves as an immense natural radiator, continually releasing heat from within our planet. The Earth most resembles the other 3 inner worlds, both in terms of its rocky composition and its history of volcanism. Mercury, Venus, Earth, and Mars, they were all formed in a similar manner. But the cooling process in each of these rocky worlds has taken a different course. Mars is the 4th planet from the Sun. Its orbit is just outside that of Earth's, but its surface is dramatically different from our blue world. The red planet is covered with craters, much like the Moon. A striking feature is the huge volcano, Olympus Mons. More than 15 miles tall, this Martian colossus is the largest known volcano in the solar system. It's evident that Mars was once volcanically very active, but those eruptions ended more than 100 million years ago. On Mercury, the planet closest to the Sun, there are signs of surface movement. Amid the craters are immense cracks that were formed when the planet shrank during its relatively quick cooling period. These sheer cliffs are as much as 2 miles high and 250 miles long, and point to a time shortly after Mercury's formation when all volcanic activity stopped. Earth is much larger than Mars or Mercury and is taking much longer to cool. Its internal heat continues to vent and reshape the surface of the planet through undersea volcanic activity and on the surface as well. Djibouti is a small country in Africa, part of the highly volcanic Afar Triangle. The daytime temperature can reach 122 degrees as winds blow clouds of dust across the bleak terrain. At first glance, this desert wasteland seems dry and geologically stable. But there is evidence that the land is in the process of being reshaped. Amid the mirages that dance across the Afar Desert lie some truly unusual rock formations. These towers, which reach as high as 200 feet, are called travertines. In the midst of the blazing desert, they periodically give off steam and hot water. Many travertines stand in neat rows following the line of underground fissures. It's no coincidence that they resemble the chimney-like smokers found on the sea floor. These inland travertines were formed by billowing smokers on the bottom of an ancient lake. They grew tall from the lake's rich mineral supply of calcium carbonate. Even today, underground water boils up into pools on the dry lake bed. It's an indication that this land is still in the process of change, fueled from the escaping heat within our planet. Because the travertines are located over a major rift or fault line in the Earth's crust, earthquakes are frequent. The epicenters of these quakes stretch in a line from the northwest to the southeast. This whole area is sinking from the seismic activity, creating a deep terraced valley. It's the northern end of Africa's Great Rift Valley that stretches almost 4,000 miles from the Red Sea in the north to Mozambique in the south. Four million years ago, the land cracked open here, creating well-watered valleys where wildlife flourished. At Tanzania's Lake Natron in the heart of the Great Rift Valley, the water is blood red. The unusual color is due to soda-rich water, forced to the surface by the hot magma below. The alkaline water kills everything but red-colored bacteria, and the sun creates patterns on the surface that change constantly. The Great Rift Valley is an extension on land of the undersea ridges that circle the globe. And like those fault lines, the valley is growing deeper as the land moves away on both sides, split apart by the heat within the earth. It's the result of what might be called the blanket effect. The landmass of a large continent holds heat better than the thinner ocean crust. The intense heat accumulates beneath the continent, trying to escape. As the heat builds, the continent rises and finally splits. Fissures appear on the surface, then a long rift valley. Eventually, the oceans fill the valley as it continues to spread. In this way, the continents have been reshaped and have drifted across the face of the globe, powered by the energy escaping from within the Earth. The familiar face of the globe as we know it today, with huge oceans separating the Americas from Eurasia, was once completely different. 250 million years ago, there was one huge continent called Pangaea. Driven by the heat within, the supercontinent split apart. Where once there was land, rifts opened and filled with water. The land continued to spread away on each side, and in time, the modern continents took shape. This process is happening today in the Great Rift Valley. Here, the land is splitting apart. Every year, the valley gets wider. The progress is slow, less than an inch a year, but it is relentless. The African continent is slowly breaking up. As the land gradually sinks and splits, more lakes will form, and eventually the sea will fill the long valley. This is how a continent begins to divide. 50 million years from now, the global map may show an African sea.
As continents pull apart on one side of the globe, they must inevitably come together on the other. In fact, continental and oceanic plates are in collision all over the world, driven by the heat within our planet. Often mountain ranges are pushed up where plates come together. The Andes of South America and the European Alps were born in this way, as was the tallest range on Earth, the Himalayan mountains.
The lofty peaks of the Himalayas reach through the clouds to the sky. The immense mountain range extends for more than 2,000 miles from east to west and covers an area the size of East and West Germany combined. The word Himalayas comes from Sanskrit and means abode of snow. This is a frozen world above the tree line. 14 peaks tower over 26,000 feet high. Among the highest are Everest, Annapurna, and K2. The Himalayan mountains touch the roof of the world. At one time, however, the rocks that make up the Himalayas were at the bottom of the sea. There is fossil evidence high in the mountains of sea creatures, like this bivalve. These marine organisms inhabited the warm seas of ancient times. Embedded in the brown stratum are the grayish remains of many crescent-shaped fossils. Their numbers testify to the richness of life in the ancient sea. In addition to bivalves, there are many other fossils of ancient sea life. Here, preserved in stone, is a crinoid sea lily. Although very small, it's an ancient relative of the sea urchin and starfish. Even more fossilized sea life appears under magnification. The large round-shaped object on the left is another sea lily, while the smaller object on the right is an ancestor of modern coral. Even smaller is the foraminifer, a primitive diamond-shaped creature that's a species of plankton. This is the cross-section of a tiny fossil snail that once inhabited the tropical seas of our planet. Elsewhere in the Himalayas, there is even more remarkable evidence of the marine origin of these mountains. The scallop pattern on this hillside is the fossilized impression of waves on an ancient seabed. It's similar to the ripple pattern found today on the bottom of shallow seas. In many ways, however, the world was a much different place when ocean waves left these impressions. Between 220 and 70 million years ago, during the Mesozoic era, the oceans of the world were inhabited by many species that are now extinct. Among the denizens of these ancient seas were tube-shaped belemnites. Ammonites were also common. Their name comes from the ancient Egyptian sun god Ammon, who is believed to have a spiral sheep's horn on his head. They're a species of cuttlefish that first appeared on Earth 400 million years ago. Today, evidence of these ancient sea creatures can even be found among the highest Himalayan peaks. From this fossilized belemnite, only the tube-shaped central portion remains. The name of this squid-like creature comes from the Greek word belmnon, meaning spear-shaped. Here, too, are ammonites, locked in stone. The fossilized impression is all that remains of a creature that lived before the Himalayas were born. Ammonites thrived during the time of the dinosaurs, but became extinct about 65 million years ago. Now the remains of these and other ancient sea creatures are found near the top of the world's highest mountains. How did this happen? It's a journey that began when this region and the rest of the world looked much different than today. This is a computer-generated view of the Earth. The 7 seas and 6 continents form a familiar picture. But this was not always the case. The continents were in different locations when the Earth was younger. By projecting back in time, the course of these wandering continents becomes clear. India, shown here in yellow, was once located in the southern hemisphere. Africa was separated from Eurasia by a broad, shallow sea. Even before this, all the continents were joined together. North America was connected with Europe, South America with Africa. On the opposite side of the globe, a vast ocean spread from pole to pole. This is what our Earth must have looked like 200 million years ago. But the heat within our planet was already beginning to drive the continents apart. It forced India northward. For 100 million years, this African island drifted more than 4,000 miles toward Asia, at a rate of 15 to 30 feet per century. Slowly, it crossed a vast, shallow sea, teeming with life. As the two land masses drew close, seafloor sediment between them was compressed and folded. A chain of small islands began to appear in the narrowing remnant of the shallow sea. Once, this island archipelago must have been a marvelously lush place. Then, 45 million years ago, it vanished forever when India slowly crashed into Asia in one of history's truly earth-shaking collisions. Barely slowed by the initial contact, India continued to slide under the larger landmass. Upthrusting began to occur all along the line of collision, pushing up the seabed that contained the remains of marine creatures. Higher and higher the mountains climbed, until they formed the tallest range on Earth. The process of continental drift that formed Mount Everest and the Himalayan peaks also created many other Eurasian mountain ranges. An interconnected chain of mountains runs from the Himalayas through the Hindu Kush and the Caucasus Range. From the Carpathians and the Alps to the Pyrenees and the Atlas Mountains. All these ranges were born at roughly the same time, and all were formed in a similar manner. The rocks that make up the fabled 38 summits of the Alps, for instance, show many signs of undersea origin. Pillow lava, which originally erupted underwater, can be found here at 6,500 feet above sea level. Here too are many limestone cliffs built up from the fossilized remains of ancient sea creatures. Even though 3,000 miles separate the Alps from the Himalayas, thousands of fossil ammonites, common to both, crowd this French cliff face. When these creatures died, their shells were deposited on the bottom of the ocean. Later, the seafloor was tipped vertically and forced several thousand feet into the air by the enormous force of colliding continents. As the African continent drove north toward Europe, the shallow seabed between them was compressed and racked into an incredible array of folds. There are places throughout the Alps where there is evidence of the powerful forces that twisted the rock, turned it upside down, and raised it toward the sky. The enormous energy within our planet gradually moves continents and pushes up great mountain ranges. This same force is also responsible for purifying many minerals and bringing them within our reach. One mineral that has long been important to humanity is copper. From the first metal tools of the Bronze Age to the electric wiring in modern homes, copper has helped shape our civilization. And yet, without a unique natural process fueled by the internal heat of our planet, copper would not have been available to lift us out of the Stone Age. The island of Cyprus in the Mediterranean Sea is rich in copper. In some places, the mineral was found right on the surface. This easy access to the copper ore was particularly important to its early discovery and use. Over 3,000 years ago, miners first brought this precious metal to an eagerly awaiting world. Copper was one of the first metals known to mankind, and the first used to form tools, utensils, armor, and art. Copper was used by ancient Mediterranean peoples to express their dreams and fears. Achilles wore a helmet made of bronze, an alloy of copper and tin, as did his opponents on the fields of Troy. During the Bronze Age, Cyprus prospered as the principal source of the metal for the artistry of Greece and Persia. Early Mediterranean civilizations flourished because of this copper wealth. The English word for copper is even derived from the ancient Greek name for Cyprus, Kuprios. The island of Cyprus and its concentration of copper originated on the floor of the ancient Mediterranean Sea. Here, along an undersea fissure, heat from the earth concentrated the copper through an extraordinary process. Below the seabed, water seeped down toward a huge pool of magma, straining to escape. As the cool seawater met the molten magma, it was heated. The superheated water percolated through the rocky crust, leaching out small amounts of copper compounds. Some of the mineral was then deposited in the surrounding seabed as the water forced its way upward. Finally, the superheated water appeared as white and black smokers. Year after year, the concentration of copper continued to build around the smoking chimneys, fired by the heat of the earth itself. Over many millions of years, the volcanic activity in this fissure forced the seafloor apart, and the rich deposits of ore were carried away. The copper deposits were brought to the surface when the copper-rich seafloor collided with the European continental plate, forming the island of Cyprus. But this is only one of the ways that copper and other minerals have been naturally refined by the internal heat of our planet. The majority of the copper produced today comes from Chile, in the Andes Mountains. Layers of light and dark rock contain a wealth of fossilized sea creatures. Like the Himalayas and the Alps, this area was also once at the bottom of the sea and then pushed up. The Andes rise along the western coast of the South American continent. Spanning 5,000 miles from one end of South America to the other, the Andes is the world's longest mountain range. Its highest peaks soar above 20,000 feet and are still growing. The Andes hold a wealth of minerals: gold, silver, tin, and copper. Almost all of South America's copper mines can be found in the Andes, because the same force that pushed up these mountains also formed the rich mineral deposits. The mineral resources found in the Andes are the result of volcanic activity. The heat rising close to the surface is evident throughout the Andes today. This steaming peak is nearly 4 miles above sea level. On the high plateaus between the peaks, mineral water bubbles up from deep underground. Even at such high altitude, the heat within the earth rises very close to the surface. Water from melting snow seeps into the rocks. There it is heated by the magma and bubbles back to the surface. Water is the key to concentrating the mineral wealth of the Andes. "40 million years ago, there was extensive volcanic activity in the mountains of the Andes. During this ancient time, there were many minerals, including copper, hidden below the surface. But these elements were scattered in very low concentrations. If the copper had remained in such a scattered form, it could not have been mined. But through a special process, the volcanic magma transformed them. Around the perimeter of the underground pool, the magma began to cool, and minerals held in solution began to crystallize. The superheated water contained in the magma rose up. The copper compounds, dissolved in the water, rose as well. The heated water gathered on the roof of the magma pool. Pressure built and cracked the surrounding bedrock. Water seeped through the fissures, taking the copper with it. As the water moved up through the earth, it cooled, and copper was deposited along the way. The result, veins of copper ore. Copper pyrite is formed by this process of water interacting with hot magma. The concentrating action of water and cooling magma has resulted in a vast deposit of copper ore in the Andes. This is the Chuquicamata mine in Chile, the world's largest copper mine. The pit is 4 miles long and 440 feet deep. But despite its great depth, this excavation only scratches the surface of the copper ore concentrated by the heat within the earth. The volcanic activity that moves the continents and forces up the mountains has naturally refined copper, gold, and other minerals. Without this first natural step, copper would be too scattered to mine effectively. But mining copper ore is only the first step in the process. The copper is still not concentrated enough for us to use. Changing solid rock into liquid may be natural enough below the thin crust of our planet, but on the surface, it is not a simple task. Today, we purify copper in huge mechanized smelters. Copper ore, which may be only 1 or 2% copper, is melted in horizontal furnaces and refined into ingots of nearly pure red metal. Knowledge of how to smelt copper was one of the crucial discoveries that launched humanity on the road to modern civilization. We've come a long way from the first implements of the Bronze Age, thanks to our ingenuity and the internal heat of the Earth. On the surface, the Earth is a temperate, hospitable world, with oceans of liquid water and a cool, oxygen-rich atmosphere. But not too far beneath the crust, our planet is very different. Inside the Earth, the temperature is hot enough to melt the hardest rock. Over billions of years, this internal heat has shaped the surface of our planet. It made the mountains and oceans, moved great continents, and concentrated minerals like copper and gold. It is responsible for hot springs under Iceland's glaciers and blood-red lakes in the heart of Africa, strange sinking valleys, and the tallest mountains. Even now, the heat from within continues to forge a new world from the material of the old.